This video is going to be pretty exciting for me because we are starting towards the introduction of binary search trees, which are really powerful. And this video is really a motivation for why those are so great. So remember, binary trees, they can really have a lot of different kinds of shapes. The important part is that it's a rooted tree, and then every node has 0 to 2 children. Okay, so you can see here we have a binary tree. It's a little wonky, like over here, a bunch of nodes with only one child, but that's fine. And in this video, we're going to talk about useful shapes. So binary trees can have a lot of shapes. Here are 3 shapes that are really useful. And each one of these shapes, the first one is full. The second one is complete. And the last one is perfect. Each one of these requirements is kind of stronger than the one before. So I want you to look at these 3 trees, full, complete, and perfect, and try to identify what do you think is the perfect node. If perfect is kind of the nicest requirement, which one of these would you say is perfect? Which one would you say is complete? Complete's not quite as nice as perfect, but still pretty nice. And which one would you say is full? Again, full trees are nice, but not quite as nice as the other 2. What would you think? Well, here is our perfect tree. Perfect essentially meaning that the entire bottom level is filled. Everything only has two children or 0 children, etc. Complete is over here. That's our middle requirement, which is, it's like as perfect as it can be, essentially, right? If we had more nodes, we can make it perfect, but, we only had this many nodes, so we completely filled every level. And then the last one, we did as best we could. We filled it left to right, but we didn't have enough nodes to make a completely perfect tree. And then full is over here, where it's just every node has 2 children, if it has any children at all. So some short definitions, not super precise, but in short, something is a full binary tree if each internal node has 2 children. In other words, no node has 1 child. That might be an easier way of phrasing it. There are no nodes with 1 child. So over here, this is not a full tree. D only has 1 child. To be a full tree, every node has to have 0 or 2 children. Over here, we have a full tree, right? There's no nodes with only 1 child. Complete is, again, not going to give a very precise definition here, but it's filled top to bottom, left to right, right, with no gaps until the end. Just as close as we can to perfect. And then perfect is every level is filled. Not super precise definitions, but just in terms of understanding intuitively what's going on, this is what we can think of for perfect, full, and complete. So these are going to be nice, and essentially they all have to do with kind of filled in compactness, if you will, of density of these trees. Because what's going to come into play, especially with binary search trees, is that the shorter the tree is, the nicer it's going to be to work with. And essentially when we have that, we have some very cool properties. So two of the main kind of specializations of binary trees when you have certain kind of niceness or compactness are going to be binary search trees, which we talk about in the next video, and heaps, which we're not going to talk about in this class, but you may have seen or heard of. So let's think about a perfect binary tree. Let's think about a tree that looks like this. In the first level, there's 1 node. Sorry, in the 0th level, if you will, at depth 0, right? In this next, now there's 2 nodes in that level, there's 4 nodes in that level, 8 nodes in that level. If we had a perfect tree with 1 more level, right, it would have 16 in that level. So perfect binary trees grow exponentially. Okay. Perfect trees grow exponentially in size. Adding a new level requires adding double the nodes of the previous level, right? Because each node has 2 children. So each node is kind of leading to 2 more nodes. It's doubling, right? And so what that means, right, is that these perfect trees grow so fast. A very common example of like how fast exponential growth is if you imagine taking a piece of paper, right? If you take a piece of paper, it's very, very small. If you fold it in half, it gets thicker, right? You fold it in half again, well, it gets twice as thick again if you folded it perfectly. And now it's in quarters. Fold it 3 times, it's in eighths, and again, it gets twice as thick. If you folded a piece of paper, if it were possible to fold a piece of paper 42 times, I just folded mine 3 times, but if it was possible to fold a piece of paper 42 times, this is exponential growth, it would reach all the way to the moon. You know, the one in outer space, the thing way up there, that moon, okay, with only 42 folds. Similarly, right, if you have one of these trees, and let's say you have a perfect tree that's 20, has a height of 20, right? So that means there's 21 levels because that first one is like a height of 0. So a tree with a height of 20 has like over 1 billion nodes, I think over 2 billion nodes, height of 20, right? They grow really, really fast. And now you might be saying, why is this a good thing? This seems like things are getting huge, really hard to deal with. And it's a good thing because of the reverse. If we have 2 billion data points, we can fit that into a binary tree of only height 20. And that's really, really nice because when we have search algorithms, if it's sorted correctly, we can search through the entire 2 billion things in only 20 steps, which is huge. We'll talk more about that in the next video. So that's basically what's going on. Some really, really quick things, right, is that, you know, if we have L leaves, that's coming from a tree of height 2 to the h. So, right, if you have a tree of height 2, there will be a perfect tree of height 2, there will be 4 leaves. Hold on, let me make sure that I'm thinking about this correctly. Yes, great, I did it right. This has height 2. Again, height 1 is here. Height 0 is if we only had this top node, the root. So yeah, if it's height 2, you're going to have 4 leaves. In general, this is the relationship. This grows really, really fast. But the inverse of that, if you remember back to your pre-calculus days, if we solve for h is log of L. And now the mathematician in me dies a little bit writing this way, but this is not a typo. I'm assured that computer scientists often write LG for log base 2. Again, I'm a mathematician, so this feels very weird to write, but it is a thing, log base 2, because again, when you're dealing with so many like binary things, log base 2 is the natural, not the common log, not the natural log. Log base 2 is usually the way to go. So this is really, really nice. And so you can use this to find the relationship between how many leaves your perfect tree has. Again, this is only for perfect trees, and the height of that tree. Now, similar things, right? If you have a complete tree, it's going to be very close to this in terms of total nodes. And yeah, if you wanted to do total nodes, I think it would be something along the lines of, don't quote me on this, but your total nodes, I think, is 2 to the like h plus 1 minus 1. I think that's it. So here its height is 2. So this is 7 total nodes. Great. Good. That's the total nodes relation to the height. This is the leaves relation to the height over here. So I'm getting a little into math land, which is pretty fun. It's not very important. The important thing for you is the relationship between height of a perfect tree or close to perfect. We'll eventually relax this to the idea of complete. Sorry, not complete, balanced. Too many terms in this chapter. That'll be at the end of this chapter. We'll talk about balanced, and that's really what we really care about. So not so much perfect, because again, you're not always going to get perfect, right? There is no way to make this complete tree a perfect tree, but complete is still very, very good. All right, that's pretty much it. We will get into binary search trees in the next one, talking about binary trees that have certain properties that make searching through those binary trees, that's where binary search tree comes from, very, very easy, very, very quick. We'll talk about how quick, and it's a fun chapter. The section, the author himself, he just goes nuts when he's writing this section of the book. He's so happy. I've never seen anyone so happy writing a book as the author is in the next section. So check it out if you want to see an excited author. I'm rambling now. I'm a little sick. Have a good one. Bye.